Okay, this is the last video of the chapter, and this is about analyzing some graphs and kind of coming up with some stories to represent what is going on in the graphs. Now, keep in mind, you could have several different stories representing the same thing. So it's not necessarily wrong if your answer is different, but it does have to make sure it follows what is going on. So this first example, we have Danielle sketch the relationship between altitude and time for one of her ski runs. Interpret each interval of her graph. So you definitely, before you start, want to make sure you're looking at the axes. Our x-axis is our time. So we would be putting in the time into this function to figure out the altitude, which is how high she is up in the air. So we can see that as she starts over here at the origin, time is 0. So she's starting right now. Okay, the altitude is 0. So she's starting at the ground. Okay, and then her altitude is rising as time goes by. So if we think about skiing, okay, we probably realize that you take a ski lift usually up to the top of the mountain. So it would be reasonable to say that Danielle is on the ski lift going up the mountain because her altitude is rising as some time is passing. So then she gets up to the top of the mountain, and we have this flat part, and we said that this is constant. So this part was increasing, but that part right there is constant, meaning her altitude isn't changing for a brief period of time. Okay, so she probably got to the top, maybe has to adjust her, skis and things like that, put on her equipment. So she's just waiting at the top of the mountain right now. Okay, before she starts doing her actual ski run. And then you can see that there is a sharp drop in her altitude. Okay, so this would be when she is skiing down the slope. Okay. If you look, now obviously the first part is a positive slope, it's increasing, and this last part was a negative, it was decreasing. So her altitude was increasing at first and decreasing at the end. But if we look at like how steep the line is, this part at the end where she's skiing is a lot steeper because when you ski, you go pretty fast. Okay, so her altitude is dropping way more quickly than it was when it was rising. Okay, rising was like a nice little ski lift going up to the top. Here she's going fast down the mountain, so it takes less time to cover the same amount of ground. Okay, that's also a good thing to note there. Okay, so next one, Jeff is practicing javelin throws. Okay, what is the relationship between the height of the javelin and time? So when you throw things, okay, this is actually getting into some algebra. So we're not going to go too deep into it, but when we throw things, it actually follows what's called a quadratic path. And that's where we deal with x squareds and stuff like that. So we're not getting into the technicalities, but it's good to know that when we throw things or kick things, they form this arc as they go up in the air. Okay, and then what happens is gravity starts pulling it down, so it kind of reaches this maximum value, and gravity pulls it back down, so it comes back down to the earth. Okay, so when we talk about throwing things, we're usually going to do it with a curve. It's not going to do the same thing as our ski lift did up there, where it's like kind of chunks of lines. Here, it's a nice curve as we throw something. And it's also good to note that where that curve starts can differ. So here we're throwing something. So you have something up in your hand. Okay, it's up in the air. So if we're looking at time and height, okay, height is how far it is off the ground. When we're throwing this javelin, it's not going to start down at the bottom at the origin, okay, like Danielle was starting at the bottom of the mountain. Okay, here we're holding the javelin up in the air, so that's why our height is further off the ground. If you were kicking a soccer ball off the ground, then that would be something. Don't draw this, but that would be something where it's starting down here and then going up and coming back down. Okay, but for here, we're throwing it from the air. So what's going to happen, he's going to throw from a height. I'm just going to jot some things down. Throws from height in the air. Okay, it's going to go up okay, until it reaches a maximum height. Abbreviate max height. Okay, and then we said gravity is going to kind of stop it from continuing to go up in the air. Okay, and then it's going to decrease in height until it hits the ground. Okay, so throwing from a certain height in the air, not on the ground in this case, it's going to go up until it reaches that maximum height, and then it's going to decrease in height until it reaches the ground. Keep in mind if this was two people playing catch, okay, maybe it never even hits the ground in the end because you're throwing it from up in the air. It's going up, 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 reaching that maximum height, coming back down, but then someone catches it. Okay, so it's not going to hit the ground in that case. So maybe in that case, our graph kind of gets chopped off right there as the person catches the ball. Oops, forgot that was there. Okay, so now we have just a couple things to fill in here. So just an important part to note that this right here, the y-intercept is the starting height. So this is the height from where the javelin is thrown. Over here, the javelin is going up in the air. It is increasing at this point. It reaches this point at the top of that curve, where we're going to call that the maximum height. And then it's going to start decreasing again. I'm going to make a note over here. It hits the ground. Okay. And the last one, just before we do it, we're going to talk about speed and its relationship to graphs real quick. So maybe in science, possibly, you learn the formula distance equals rate times time. Okay, rate is just another word for speed. Okay. If I rearrange that formula and get r by itself, okay, to get speed by itself, I would divide both sides by t, which means speed or rate is going to equal distance divided by time. So a lot of times you're going to encounter graphs where, okay, we have our x-axis is distance. Sorry, scratch that, said that backwards. Our x-axis is time. Okay, 1 second, 2 seconds, 1 minute, 2 minutes, and keep going. And then our y-axis represents distance, how far something travels. So if you are looking at maybe a line that looks like this, okay, and you find the slope of it, okay, the slope you would find, the change in the y's over the change in the x's, right? But that would really be the change in the distance over the change in the time. And that means that that is really your speed. So in a graph, if you have a time and distance graph like this and the steepness of it tells you how fast something is traveling. Okay, so something like this is, pretty constant, like a normal speed, I guess. I shouldn't say constant. Constant is different, but it's a pretty normal speed. If we had something traveling really slow, it would look more like this because its distance is going up very slowly as time goes on. If something's going very fast, okay, it would be even steeper than our purple one. Okay, so when you're talking about speed, okay, you can kind of adjust the slope of the line to show in relativity how fast something is going. Okay, we're not going to be exact here, but we can definitely show when things are slower versus faster. Okay, so our last one here, Harry rides his bike from his home for 30 minutes at a fast pace. He stops to rest for 20 minutes and then continues in the same direction at a slower pace for 30 more minutes. Sketch a graph of the relationship of Harry's distance from home over time. Okay, so good things to note here. Like I said, there's no numbers on this. We're not going to be super exact, but he's riding his bike for 30 minutes, stopping for 20, and then riding again for 30 more minutes. So the two bike rides should be lasting approximately the same amount of time on the x-axis. And that stop time is just gonna be a little bit shorter. Okay. So he's riding at a fast pace, it says. So I'm going to say from here to here is pretty fast. Okay. And then he stops for 20 minutes. So that means it's a constant, it's flat, it's not going anywhere because his distance doesn't change. Okay. So I'd say that's pretty good. And then he keeps on going for another 30 minutes. Okay. But slower. So when I do this section, I want to make it not as steep as my first section. So I'm going to just go a little bit more like that instead. He's still riding, but this is not as fast as that first part there. Okay. These will take a little bit of practice. Okay. So just do your best. Okay. Look at the axes, see what they represent. Okay. And then go from there.